For this lecture, we will review quality control and determine what we do with those values now that we have looked at the statistical data, figured out how to do those calculations. We're going to apply it to the quality assurance and quality control within the clinical laboratory. In the clinical laboratory, part of our role is to ensure that we are sending out quality and accurate results. So in order to do that, we often have to look at the various instruments and methodologies that we use within the laboratory, and we've got to monitor those to make sure that we are sending out accurate results. So the quality assurance is the process in which all of this happens. It is the process in which we're monitoring all these different activities. And so those activities can actually be divided into 3 different phases. The pre-analytical activities before the sample reaches the laboratory, the analytical activities once it is in the laboratory and it's being analyzed, and the post-analytical activities, which is once the analyte or the test is ready to be resulted. So we have to monitor all 3 of those phases and look at the different aspects of all of those phases of testing in order to ensure that we're doing what we're supposed to do. So those activities that happen before the sample reaches the laboratory, those are the pre-analytical activities. And so this is going to deal directly with the collection of those samples. So if you have an error in the pre-analytical phase, then that's going to be something happened with the drawing or the transport of that specimen. Let's just say the sample was collected from the wrong patient and labeled wrong, or the sample wasn't spun and it's set with the plasma and the red cells touching, so you had some the different analytes maybe have seeped out of the actual red blood cell and could be affecting your results. Maybe it was left in a hot car. So all of these are pre-analytical issues that can affect that sample quality, which in the end, the result is only as good as the sample. Now, an example of an analytical activity would be something that happened while you were testing. Maybe there was a bubble that was sucked up into the analyzer, so it gave you a false result of something. Maybe QC failed for the day. Maybe there's some kind of error that's going on in the room, like the temperature has gotten too high in the room. Maybe there was a power failure while that sample was running through. So these could all be issues that happen while the testing is actually taking place. And then your post-analytical activities, of course, are going to be once you're ready to result that. So let's just say that, for example, you did a dilution, a manual dilution. You ran it on the machine, but you forgot to tell the machine that you actually did a manual dilution, and so you didn't do that calculation before that result was sent out, and maybe it got sent out. So that would be an example of a post-analytical error, that you didn't do what you were supposed to do to make sure that an accurate result was sent out. So when we look at the quality in the lab, we're going to look at all of these different phases, and usually most labs will have a variety of activities in place, different ways to check this, different aspects of the phases of testing, could be different audits and things like that. But of course the QC material or the QC values when you're assessing whether or not an analyzer is functioning properly is also going to be a big part of this. So one of the main methods that we use in the laboratory to assess quality is to run quality control. So when we run quality control, we have to use a material that is ran and analyzed just like our patient samples would be. So it needs to be treated just like a patient sample. That also means that that material should be the same matrix as the patient sample. So when we talk about matrix, this is a term that we use to refer to the chemical and physical characteristics of the material that contains the particular analyte that we're looking for, that we're measuring. So if the measurement of the analyte is serum, then that quality control base needs to be serum based. That material needs to mimic what serum is. Likewise, if we're measuring something in the urine, and then we need to make sure that that material is the same consistency characteristics as a urine sample. So the manufacturers will develop a quality control material that will match whatever you're testing. Now there are a couple of different matrices out there that they use for this material. One of them is lipolyzed or it's freeze dried, so that material will have to be reconstituted before you can use it. So you actually have to add some sort of diluent to it to reconstitute it, and so that it turns into the more liquid form that we're used to seeing. The second form of quality control material is an actual one that's actually in that liquid form. It's pre-diluted, it's ready to use. You basically just open it up and put it on the machine. And then there's another form that is an ethylene glycol based that is also used. And that particular material can't be used for certain test analytes, but your laboratory will determine what they're going to use, and they will do all these values. This is not typically something that would be placed in the hands of an MLT to make these decisions and to determine what materials you use. This is going to be determined before you ever get there, but just know that there are different materials that are used, so you may have to do some sort of preparation process or step in order to reconstitute or to prepare these control materials for testing. Obviously, if you've got to reconstitute something with a diluent, if you measure that incorrectly or you don't allow it to properly mix, so you always got to follow the manufacturer's instructions. So if it tells you to reconstitute with a particular diluent, you make sure you use that diluent, you make sure you use the adequate volume that the procedure tells you to do, as well as letting it sit, come to room temperature, anything like that that it has in the prep of that particular material. Make sure you follow those directions. If there's an error, then obviously your QC material is not going to be right, which means your values will be off, and you've just ruined your whole day of trying to prepare to run your patient sample because your QC doesn't work. So again, we've talked a lot about this Gaussian distribution curve and that confidence interval being in the center there. So I'm not going to go over this too much, but we do know that our patient's results have to, we can't send out patient results for the day until we know that our QC is in for the day. And so you do have to follow the CLIA regulations and the various standards that are set within your laboratory, as well as the manufacturer of the analyzer or the particular test or analyte that you're looking at. You've got to follow those directions for how often to do QC and things like that. But we're looking for those results to fall within those standard deviations, and we use those Westgard rules to determine if QC is acceptable. Now, an out-of-control result is a result that falls outside of those established reference ranges. Now, we've gone over in a lot of detail in the statistical math of how we actually get those calculations. So now we're talking about how we're applying that data to the different rules that we've previously learned. And so what we're looking for is to find out if the QC is out, then what caused that QC to be out. So we look at two main reasons why something may be out. And so it can be due to a random error or a systematic error. Now with a random error, this is something that just happens by chance. And so it could happen for a variety of reasons. And of course it is related to the precision of the method. But for example, it could be something that just happened, like a bubble was siphoned up, and so it happened just that one time. You can't really explain it. Maybe you can. You may not always know what happened, but if you get a result that's kind of just a weird random result, then you might need to repeat it just to see if it happens again. So an example of this would be maybe your pipetter is set to deliver 100 microliters of the sample. However, something happened during that analysis and it only delivered 90 microliters. So again, maybe it hit an air bubble, your sample wasn't sufficient enough, so that probe, when it went down into that sample, it got a little bit of sample, but it also got a little bit of air, because if your sample was a short quantity or anything like that, then obviously that's going to affect your result because you did not get the full volume of that sample to get you those results. So that will be an example of a random error. A systematic error, on the other hand, it's going to be something that's going to affect all of your samples. So this could be something that's happened on board. Maybe you've got a cooler or something on board that has failed, and so your reagents aren't staying at the proper temperature. And so that's going to affect the quality of that particular reagent, and then and ultimately it's going to affect your test. And so this is actually related to the accuracy of a method. So again, accurate, how close are you getting to that mean value or that expected value if you were to repeat it over and over and over again. And so there are a variety of things that can cause it to be a systematic error. So with systematic errors, this is where a QC is going to start catching some of those things. So you're going to start seeing some of those rules violated within your QC data. And you may start to see shifts and trends and things like that are going to happen that are causing those errors. So that should alert you that you need to do something about it. So some of the things that you might need to do might be something like calibration or routine maintenance. Let's just say that you've got probes on your analyzer that need to be changed every so many months. Maybe somebody forgot to document that they did it, or they didn't do it, or maybe it's just being used a little bit more, so it's kind of gumming up a little bit quicker. So it needs to be changed. Maybe you need to recalibrate. You know, there are a variety of things that can cause it. Maybe the room temperature, you're noticing that, certain times of the day you're starting getting some random results, and maybe a certain time of the day the room's getting too hot, and then it's causing everything on that machine to start shifting a little bit, and so you're starting to see those shifts and trends and things start to happen. And so that alerts you that maybe something else is going on that you need to investigate. So again, there are a lot of things that can cause random errors and a lot of things that can cause systematic error. It is your job as the tech to notice when something is out and start doing your investigation. And one of the main ways that we do that is by quality control. So when we talk about quality control, the way that we're going to look at all of that data that we've calculated and determined what our standard deviations are, we're going to look at all of that on a Levy-Jennings charts to assess if those values are in for the day. Is QC acceptable for today or for the shift, or whatever your limits are set. Whatever your QC values are set is, we're going to look at them on the Levy-Jennings chart, and we're going to use the rules that are established by the CLIA 88 in order to make sure that we are following what we need to. So CLIA does state that we have to use 2 levels of quality control material for each day of testing for anything that is non-waved. Now there are certain analytes that may require 3 quality control values. This is all going to be stated in the CLIA rules for each particular department. Also, your manufacturer is going to alert you to anything that needs to be done in addition. So your manufacturer may state that you need 3 levels of QC. And of course, there are some other factors that play into whether or not you use 2 levels or 3 levels, which includes some validation studies and things like that, which are generally going to be done by someone else in the lab that has a little bit more of that knowledge of how to establish those values. So as MLT techs just starting out, this isn't really something that you're going to be in charge of doing. Eventually down the road, possibly. But for now, we're just going to focus on the Levy-Jennings chart, getting that set up, and understanding what CLIA states as far as those rules. So again, the results for the quality control material should be analyzed to determine if the method is in before you actually send out patient results. And so we're going to plot our data, and we're going to look at it at the Levy-Jennings charts and use those Westgarb rules to determine if that quality control is acceptable for the day. So now let's do an example of actually plotting a Levy-Jennings chart. So here For this particular example, 3 levels of control are run daily, so that's going to be a low, a normal, and a high level for a hematology analyzer in a POL, or a physician's office laboratory. So we've already got our values and determined that our mean for this particular QC normal level is 15 or 15.0 milligrams per deciliter. So we've got that documented here on the side, so that's going to be our center point. And then, of course, standard deviation is 1.5. And so we record this data for each day of the month, so days 1 through 5. And so if we go ahead and plot out our chart, we make our chart, we've got our days at the bottom, we've got our values to the side. Our mean is 15 milligrams per deciliter. So if we add 1.5, then 1 standard deviation gives us 16.5. And then if we add to that, that gives us our 2 standard deviations and then our 3 standard deviations. Now, in order to get our negative side of it, or to expand our range, then we would do a -1 standard deviation. So 15 minus 1.5 gives us 13.5, minus 2, and minus 3. It's a little hard to read there. So 1 standard deviation, 2, and 3. So once we've plotted our chart, we've devised our chart, then we can actually fill those values in. So what will the Levy-Jennings chart start to look like once the technician starts plotting those normal values over that 5-day period? So here we've ran it, we've got those values, and let's continue to the next chart. So we have those values here for day 1, where we plotted it at 13, day 2, day 3, day 4, and day 5. So we've plotted all of those values. Again, here's our mean at 15.0, and then this is 1 standard deviation, 2, and 3. Now, when I actually plot my values, sometimes it helps to kind of color code it. Not always, but we know our mean is there. So looking at our Westgard rules, typically anything within 1 standard deviation is good. So 1 standard deviation, I kind of visualize that to still be within the green. And then you kind of have a cautionary period at 2 standard deviations. So usually once something is kind of in that point, we've got to look a little bit more detail in those rules. And then, of course, if something reaches 3 standard deviation, that's definitely our, whoa, something's wrong. We got to stop and take a look. So right now, looking at this data, these first 2 here, getting kind of questionable when we're looking at those, as far as, we're going to have to look at those rules a little bit more, but most of the data is within. So now let's talk a little bit about shifts and trends, what they mean. So when we talk about a shift, something is shifted on one side or the other of the mean. So this happens when your QC results are on one side of the mean for about 5 to 7 consecutive days in a row. And this is because of some sort of systematic error. So again, where I've kind of mentioned that you've got things that can happen. Maybe your QC material is getting old. Maybe someone didn't reconstitute it right. So this is why it's important that you're always documenting everything that you do. When you open a new vial of QC or reagent, that you document on that vial the date and your initials, so that if you start seeing any kind of trends or shifts or anything go on, then you can kind of start tracking it back. So you could look at your QC material. Did this start happening once we opened up a new lot of QC or a new vial of QC? Is it something on the instrument that's malfunctioning that you need to look at? So you've got to find the cause of whatever's causing this stuff to start to look out of control, and you got to fix that problem before it gets to a point where it shuts your whole analyzer down and you're not operating for the day. So you've got to be aware of shifts and trends so that you can see that a problem is getting ready to happen. Now, yes, these values probably did not cause any other additional flags within your value, but you can see that everything is staying on this side of the mean. Um, everything is within that one standard deviation limits, or just barely outside of it. Probably if we looked at those rules, they really wouldn't violate it. But once you kind of start seeing everything stay on one side of that mean, then that means you might need to start looking at some things that need to be done. So a trend happens when you have a decrease or an increase that's very consistent over a 5 or 7 day period. So with your shift, everything just kind of shifts to one side. With your trend, it's just a constant, steady going in one direction or the other. So this tends to be a little bit more slower because it's happening over time. But again, it's one of those things that you got to find the cause and correct it. So again, this could be something with the stability of the reagents or stability of the QC material that's starting to shift, and you can tell where over time it's just getting worse and worse and worse, and we reach the point that we need to start doing some investigation. So ultimately, each laboratory is responsible for establishing their own criteria of whether or not they're going to accept or reject any sort of quality control results. However, CLIA does state that you have to have a minimum of 2 levels of controls for each method of testing each day, unless you have some sort of equivalent quality control or the IQCP plan that's in place. And so at minimum, the QC procedures must follow the manufacturer's instructions, and you must have done the studies to make sure that you have determined that you meet the current CLIA regulations, or you've developed the IQCP and you are able to prove that your current quality control plan is effective enough to catch any sort of errors. So what the IQCP does is it's divided up into kind of 3 parts. And so you do a risk assessment where you're looking for the identification and evaluation of potential errors or failures that can happen. So you've actually got to look at all phases of that testing process, and you have to determine where the errors can happen and what kind of potential outcome you could have because of that error. Is it going to affect the patient? Could it possibly cause harm to the patient? How significant is that harm? Could it result in a sentinel event or the death of a patient? So your quality control plan, the other part of it, the quality control plan describes the lab's role for that particular test method. So you got to establish what you're going to actually use as the control and the check for that particular method, and that quality assessment plan has to be in writing, and you have to make sure that everyone follows it, that everyone is doing what they're supposed to do. So you have to do the studies in order to put the IQCP in place. If you do not do the studies, then you've got to run your QC daily. Now, does this take away from if you developed an IQCP plan for a particular analyte, does it take away from you still having to do quality control? No, it does not. It's just for certain procedures where the manufacturer has determined that this particular analyzer, for example, iStats. iStats are a point of care test that can be done bedside, but a lot of places will use them as their chemistry test panel or troponin test panel in the ER, different things like that. So because of the prep process and the steps that are involved with that actual testing of that sample, it is considered a high complexity test. Now granted, your cartridges have built-in quality control in them, and it has different checks and balances that it does each time you run a test on that iStat machine. You still have to establish that it is acceptable, that anytime that it runs a test, that there's a low risk of it actually sending out an invalid result. So you do these IQP studies because the manufacturer says you only have to run QC for X amount of days or for every 30 days. And so every 30 days your analyzer will alert you it's time to run QC again. So you have to have done the studies to say that this machine maintains its accuracy for that 30 days. Despite the fact CLIA says I'm supposed to run QC, 2 levels of QC daily for a moderate complexity test, which the ISTAT has been deemed to be, the manufacturer says, hey, that's not necessary. So I still have to establish that I did QC like I was supposed to, that yes, it did follow these rules. I've done the studies, I've put things into place to prevent errors. So now this is our plan for the ISTAT, because the manufacturer says we only have to do QC this amount of time. Anyway, that's kind of sum up a very complex thing. You probably won't be involved in IQCP. I hope not. It's a very long, tedious process. Most labs have already done and established this if they're going to, but it is possible that you could be on a team that has to do an IQCP, or you may be responsible for it in the distant future. So I know you've had a lot of information thrown at you. We've talked about the statistical data, doing all those calculations, making the QC charts. It's all confusing because at this point it just looks like a bunch of numbers and you're not really sure what to do with it. Well, the next thing that we have to look at is the rules of how we assess those values. What do we do with those values? And so we use the Westgard rules in order to determine, do we accept the QC run for the day? Do we just consider it a warning for the day? Or do we need to investigate some problems and not send out our patient results? So we use these rules to kind of assess when we start seeing things go wrong. So the first thing that we've got to do is to look at the rules. We got to follow them step by step to determine if any of those rules are broken. Is it just a warning to us, or did we determine that that particular value for that analyte is out of control for that day, so we need to do some investigation and troubleshooting. So we need to kind of understand what these rules mean. So we have discussed these before, but we will discuss them again. So those larger numbers actually mean the number of QC results that are out of control. So what I mean by that, for example, of course, the subscript numbers mean that the standard deviation, or what standard deviation has been violated. So when we talk about these rules, a 1-2S rule. So the 1 actually stands for, which is the larger number, the number of QC results that have been violated or that's considered out of control. So this particular one, we only have one result, or one QC value that is out of control. But these subscript numbers here, this 2S, means that we have one value that is 2 standard deviations outside of the mean. So that's what that particular, those numbers mean. So now let's look at the actual chart. So here again, we have that first rule, the 1-2S, meaning we have one value that is outside of 2 standard deviations. So the fact that we have one value outside of 2 standard deviations, if we have violated that rule, so if we say no, it's within 1 standard deviation, or it hasn't even crossed the 2 standard deviation line yet, then we can consider it in control, run the result. If it did violate it, of course, we do have to go through all of these results. Despite the fact that this wasn't violated, we still need to make sure we don't have any sort of warning rules going on. So we still need to look at the rest of these values to determine, do we reject the run, or do we just consider it possibly a warning for now? So again, the 1-2S rule, that means that that particular value of either of your controls, it doesn't matter if it's the high or low, and again, some labs may run 3 controls, but when we're kind of comparing these, we're looking at it, at least 2 values have to be within. So one rule is violated if either of the 2 controls exceeds 2 standard deviations from the mean. It doesn't matter if it's plus or minus 2 standard deviations. It just has to be outside of those 2 standard deviations. So remember when I talked about 1 standard deviation, I kind of do that as a green, whereas 2 standard deviations means I need to be on alert. So once we've crossed over those 2 standard deviation, that's where our alerts definitely need to start popping up. So when this rule is violated, the other rules are applied. So we've got to look at these values individually, but we also kind of have to look at them as a group as well. If the quality control does not violate any of the other rules, even if one of the 2 results violates the 1-2S rule, the control can still be acceptable. So again, that kind of goes back to that chart. So let's talk about this in a little bit more detail within an example. So the following example, there are 2 Levy-Jennings charts for level 1 and level 2 glucose. But let's look at day 5. So day 5 of this chart is here. So again, we've talked about kind of our little warning here. So we've got to look at day 5 or run 5, both of them together. Do these rules violate the rest guard rules? So we're looking at day 5. So again, we're looking at our day 5, and again, our 2 standard deviations. We kind of considered our, definitely got to step up and take some action, standard deviation. And so again, we're looking at day 5 to determine exactly what we're going to do with day 5 results. Get those highlighted here so we can assess them properly. So we're just looking at the day 5 for now. We do know that we violated the 1-2S rule because we do have this one value that is outside of 2 standard deviations. That rule is violated, but again, that's our warning rule. So we have to look at our next rule. Do we have one value that is outside of 3 standard deviations? Well, day 5, we didn't get that far. And then we would continue to go through the rest of the rules. If no other rule is violated, then we just kind of consider this as a warning, keep a watchful eye on it, and then we will accept those results and we will send out patient results for the day. And so again, we're going to look at some of these other rules. This particular incident here, nothing else is violated, but we are going to talk about the other rules. Our 1-3S rule means that one of the 2 quality control values is outside of 3 standard deviations. So we've definitely hit that red mark. If a result is outside of 3 standard deviations, then that means less than 1% chance that that result is actually accurate. Remember that 99.7% rule, that everything should fall within that? Well, if you've got that 0.3% that is falling outside of those, or they are outliers, something's wrong. This has to be rejected. It is out of control. We cannot accept it. Usually this is because of some sort of weird random error. Let's just say you mixed up controls. You put the normal in place of the high and the low in place of the normal. It gives you all sorts of crazy results if you mix up those QC. So let's just say that maybe that's what happened, or an error bubble or something like that. And so usually repeating it will correct that, but if repeating it does not correct it, then you've definitely got a major issue going on. So here we have an example that we're going to look at for level 1 and level 2 of a cholesterol control, and we're going to look at day 7 of this. We're trying to determine, is day 7 violated? So again, let's move to our next chart here. So on day 7, of course, we want to kind of get us a little color code going on here where we're going to kind of determine our standard deviations. So we know that this is 2 standard deviations here, our 2 standard deviation line, and then of course our 3 standard deviation line. And look at there, we got it all the way outside of our 3 standard deviation line. Because we've violated the 1-3S, you know, of course, first we look at our 1-2S. Do we have one value, we're looking at day 7, that is outside of 2 standard deviations? Why, yes, we do. On our level 2 cholesterol control, we've got one that's surpassed the 3 standard deviations. So because of that, we would automatically reject the 3 standard deviation. So 1-2S rule was violated, moves us to our 1-3S rule. That is violated, so that we know that we've got to reject it. Yes, we could keep going at all the other rules and see if anything else is violated, but right off the bat, we know that we would not accept this. We need to repeat this control, possibly do some investigation. The 2-2S rule just means that you have 2 data points, 2 control values that are outside of 2 standard deviation. So this could be violated 2 ways. Either one control result exceeds 2 standard deviations in the same manner as the previous run. So when we talk about within a run, that means that you put both levels or all levels on for the same time. So this was, both levels ran at the same time. If you talk about a sample being across a run or the previous run, it means, you have this day and you have a next day, or you ran it for your AM shift and now you're running it for your PM shift. So that would be consecutive runs or back-to-back runs. So there was a period of time in between those 2 runs. But if we talk about within a run, we're talking about everything that was run during that particular time frame, whether it be your morning run, your afternoon run, or whatnot. So just so we're clear on what the run actually means. So in this first one, if both control results are in either that are either greater than 2 standard deviations or less than 2 standard deviations from the mean, this is kind of confusing how it says greater than or less than. So it's actually meaning greater than plus 2 standard deviations or less than, or basically outside of that -2 standard deviations. So it's not, don't let that make you think that this less than means 1 standard deviation. It actually means that negative side of the standard deviation. And then it can also mean, so this is comparing 2 control values. So it would be like a high and a low value, or a normal and a high value, normal, abnormal. If the second one is talking about consecutive back-to-back runs, so AM versus PM, or day 1 versus day 2. And this just means that you have one of those values exceed 2 standard deviations. So you could have 2 standard deviations from the mean, or you could have 2 standard deviations for both controls. So an example of this, we are going to look at day 10. So day 10 is here for both level 1 and level 2 of this particular analyte, which states that it's creatinine. So we know that both of them have exceeded the 2 standard deviations. So now let's look at the actual rule. So on day 10, both level 1 and 2 exceed 2 standard deviations, and of course it exceeded that plus 2 standard deviations there. But if we follow the rules, of course we'd start with the 1-2S. Do you have one value that is outside of 2 standard deviations? Yes, we have it for control 1, but we also have it for control 2. But we would proceed to the 1-3S. Are either of those outside of the 1-3S? No, so we would look at our next rule. That brings us to our 2-2S. Do you have 2 values either within the run, meaning the same day, or across the run that exceed 2 standard deviations? So let's look at that particular rule. So both controls exceed 2 standard deviations from the mean. So we know right off the bat that there's an error and that we need to actually investigate. Is there something that caused this? usually if you see a spike with both of them like that, that leads you to believe that something happened between the previous run or the previous day to today. So it could be maybe again you changed your QC reagent or something, or somebody didn't reconstitute something properly, or they didn't pipe that properly. Maybe they didn't pipe it enough diluent. So regardless, you do not report the patient results, and you've got to figure out what is actually going on before you can send out any of those patient results. So here we have an R. So R actually stands for range, which means that we have a range of 4 standard deviation. So when the difference or the range is between two controls within a run, so you ran them both at the same time frame. You ran your normal and abnormal at the same time frame, so maybe your morning run, and you have a difference between those two of 4 standard deviations. So when both control values violate the 1,2S rule, but in opposite directions, then that's going to create that gap that you need for that 4 or R4S, that range of 4 standard deviations to be violated. So that means that one of the controls is greater than 2 standard deviations, and one of them is going to end up having to be on the negative side of those standard deviation. And so this is usually going to happen because of some kind of random error. You can see this if you switch up your controls as well. That sometimes does happen. So here we have our example, and we're going to look at day 12. So let's talk about those rules. So on day 12, control result for level 1 and level 2 were ran. And as we can see, they both violated the 1,2S rule because you have one outside of the 2 standard deviations. Both control levels violated that, so that means that we've got to look at all the additional rules. Do either of them or either value outside of 3 standard deviations? No, so we move to the next rule. Or either value outside. Do you have 2 of the values outside of 2 standard deviations? Well, yeah, technically we do, because it's within the run and they're both outside of the 2 standard deviations. So let's keep going. Do we violated the range of 4 standard deviations? So if our level 1 is above the 2, and then we have to go 1 standard deviation, 2 standard deviation, 3 standard deviation, 4 standard deviations, yes. So within that run, we have a range of 4 standard deviation, which means that R4S rule is violated. So moving on to our next rule, do we have 4 data points that are outside, or 4 consecutive data points that are outside of the 1 standard deviation? Of course, we can look at this 2 different ways as well. It can be within consecutive runs, so the same level, 4 runs back to back, they're all outside of 1 standard deviation. Or it could mean between the 2 levels, the normal and abnormal, that we have for 2 consecutive runs. So we got to compare both data for 2 days or 2 consecutive runs back to back to see if within both of those, the normal and the abnormal, do we have 2 value points that have exceeded the 1 standard deviation to give us a total of 4. So this is kind of similar to the shift rule, the 4 results on the same side of the mean, which is statistically unlikely, but they exceed the 1 standard deviation, but not quite 2 standard deviations. So let's look at that in application. So here we have an example that we're looking at 2 levels of control for bilirubin. And so we're going to kind of evaluate these to see if it has violated any of the rules. So let's look at those rules. So let's look at our current rules to see what we have violated so far. So our 1, 2 standard deviation, do we have 1 value outside of 2 standard deviations? No, we don't, but we still have to assess the other rules, correct? Now we're looking at the 1,3S. Do we have one value that is outside of 3 standard deviations? No. Do we have 2 values that are outside of 2 standard deviations? Well, we don't have any value right now that's outside of 2 standard deviations other than we did here on this day 1, but we're not really evaluating that. We would have evaluated that on day 1. So we're looking at day 4. So we do not have 2 values that have violated on day 4 that 2S rule. So we're at our range rule, range of 4 standard deviations. Well, we know that we've got to be at least have violated the 2S rule in order to even hit the 4S rule, which we haven't. So we keep going. So now we're at the 1S rule. Do we have 4 values that are outside of 1 standard deviation? Again, this can be consecutive with within consecutive runs for 1 level, or it can be within 2 runs for the 2 levels. So the control result for day 4 does violate this rule because we do have 4 consecutive that are outside of it. And then if we were to look at the 2 consecutive days for our level 2, neither one of these are outside of that 1 standard deviation, so it doesn't violate it with looking at level 1 against level 2, but level 1 is definitely violated 4 consecutive runs on one side of that standard deviation. So this is kind of considered a systematic error. It's most likely the reason, and the run is rejected until we can figure out what the problem is. More than likely for something like this, it's just kind of shifted over time, and maybe the analyzer needs to be calibrated again. So once you calibrate, get everything back in line, then this will clear up. All right, and now we have the 10 consecutive run rule. So this can be violated 2 ways as well. So again, we've got to look at it within consecutive runs or consecutive days, back-to-back runs for one particular level. And so those 10 results for that one level fall on either side, positive or negative, just consistently on one side of that mean. And the other way you can look at it is look at both levels, the normal and the abnormal level, to determine for each of those if you have 5 runs, 5 consecutive runs back-to-back, or 5 days, 5 shifts, in which those controls run on the same side of that mean. So here we have an example. We're going to look at the various rules to determine which ones are actually violated. So here we're going to run through these rules again with our 1-2S rule. Do we have anything that is outside of those 2 standard deviations? Remember, I like to kind of put in my cautionary rule here, just so it kind of gives me a quick overview. No, we do not have anything outside of 2 standard deviations. Here's our 1 standard deviation here. So plug those in for both of these, just so we'll have a visual. All right, so 1-3S, well, nothing violated the 1-2S, so we're going to keep going. Now we're looking at our 2-2S. Do we have 2 values outside of 2 standard deviations? No, we've still not violated that. Our range of 4 standard deviations, well, if nothing's violated 3, it's kind of hard to violate that 4th one, or that range of 4. Do we have 4 values outside of 4 consecutive values outside of 1 standard deviation? So if we look at this within each slot or across runs, we still don't really have, for level 1, nothing in those 4 days or the 2 days violates the 1S. Within the 4 days, we do have that 1S, but it's not consecutive violating. So that rule, the 4-1S rule, is not violated. So now we're up to our 10X rule. Do we have 10 consecutive values for one run that are all on the same side of the mean? Or do we have, within the two QC levels, do we have 5 that are on the same side of the mean? So automatically we see where our mean is here, and that our level 1 is kind of bouncing up and down. It's kind of going over it, which is what you want to see. You want to kind of see that little heartbeat. Whereas the level 2, you can see that we have several values that are all on the same side of the mean. This means that there's some sort of systematic error that's happening within that level 2, and it could just be the quality of that level, because level 1 is doing as it should. So that doesn't lead me to believe that there's anything really major going on with the analyzer. It seems like it's pointing more towards this QC valve, maybe the stability of it. Something's not quite right. Maybe it wasn't reconstituted properly. So you would need to do some troubleshooting. It still could be the analyzer, something that's going on in the analyzer, but more than likely just getting a new QC valve will kind of help with this. So again, you kind of got to compare your QC levels and look at them individually as well as together in order to be able to fully evaluate those results. Now, for whatever reason, if a lab does need to run 3 levels of control, whether it's due to the particular methodology, the validations that are performed, or whatnot, there could be situations where you have to use 3 levels. And so you do sometimes have to use a little bit of a different rule when you're looking at 3 levels. And so you have to assess 2 of the 3 values within those 3 controls in order to determine if anything violates those rules. So if 2 of the 3 actually violates the 2S rule, so 2 values outside of 3 standard deviations, 2 of the 3 levels exceed 2 standard deviations in the same direction, then that rule applies. QC is rejected. You have a 9X rule. When you have 9 results in a row for a single control that are on one side of the mean, or within the 3 different runs, the results of all 3 levels of control all fall on the same side of the mean. So that run for that day, they're all on the negative side of the mean, or they're all on the positive side of the mean. So you do want some variations there. The 4-1S rule is not used when you use 3 levels of control. So just do keep that in mind. And of course, your institute that you work for will have these rules in place as far as to help you make these decisions and calls of what to do when. So here, here's a chart that kind of walks you through those rules again for when you're looking at those values of 3 data points or 3 QC levels.